So today we're going to introduce concurrency in actors. And let me introduce the last lecture task. Now this lecture task you could have already done with what you know. But just so I'm only introducing one lecture task per lecture, I waited until today to officially introduce this one. So this is very similar to lecture task 5, except you're making a cost function for playlists instead of songs. So in the playlist object, write a method named cost function that's going to follow the same structure as the cost function for songs. And this method is going to return a function which is itself the cost function that you'll use in AO1 if you choose to accept that task. And this cost function is going to have a way to compute how good or bad a playlist is, with a higher cost being a worse playlist. So the question is, how do we generate the cost of a playlist? The structure, like I said, is the same. You're going to take a map of strings to ints, which is a specific user's ratings of a variety of songs. And then the cost of a playlist, you're going to return a function that takes a playlist and returns its cost as a double, is going to be its raw cost times some multiplier. The raw cost should be simple enough to compute. It's going, assuming you have lecture task 5 complete, it's going to be the sum of the costs of all the songs in the playlist. So you can take your song object, so you can say song dot cost function, get the cost function for this particular map, and that's going to take a song and return its cost, and then sum up the output of that function for all of the songs in your playlist. That's going to be your raw cost. So as long as you have LT5 done and it's working 100%, this should be get a cost function, a song cost function, given this map of strings to ints, and then for each song in the playlist, get its cost, and then sum all those up. By the time you get to LT6, that shouldn't be too big of a deal. You should be able to handle that. Not saying it's objectively easy or simple, but that's something that you should be able to handle. At this point, I think it's easier than some of the previous stuff, especially LT4. It's easier than LT4, figuring out how to do this. You don't even need recursion here. I could see how you could use recursion here. That'd be fine. But you can get away with just using your data structure functions and using some first order function magic in here. And then the multiplier. First, you're going to check if the playlist contains a duplicate song based on YouTube ID. So if there are 2 songs in this playlist that have the same YouTube ID, we're considering that a duplicate song, and the multiplier is 1,000, which is to say it's going to have a ridiculously high score, and we're just not going to allow playlists to have duplicate songs. It's not an infinite score, so if we're choosing from a list of songs where it's not even possible to avoid duplicates, fine, we'll accept it. But we're going to avoid it at all costs. If at all possible, we're avoiding it. If the playlist does not contain a duplicate, we're actually going to compute a score. And we're going to compute the cost of a playlist, the multiplier for a playlist, based on the standard deviation of the average energy ratings of each of the songs. Which is a mouthful. Make sure you look through each step. There's a few layers of things going on here, so make sure you look through each layer and see what's going on here. Each song is going to have a list of ratings, and each song has an average energy rating method that I provided as an example for LT1. So you can call that average energy rating method to get the average energy rating of each song. And then once you have the average energy rating of each song, you take the standard deviation of those values, and that's the standard, and that's a measure of the variance of energy in a playlist. So that is, and then we're going to reward a higher standard deviation. So that's to say that we are rewarding playlists that have a lot of variance and variety in the levels of energy. So we don't want a lot of high energy songs. We don't want a whole lot of low energy songs. We want a good mix of songs. We want a high energy song, then a low energy song, and generate our playlists that way. And then if the standard deviation is below 0.5, again, we're going to put this to a high value, not as high as a duplicate song, but we're going to say that let's penalize that by quite a bit. We're going to set the multiplier to 10. if the standard deviation is greater than or equal to 0.5, we're going to set the cost multiplier equal to the inverse of the standard deviation. So 1 over the standard deviation. Multiply raw cost by multiplier, and that's the cost of the playlist. So quite a bit of a decent amount of math going on here. Not a ridiculous amount, but a decent amount of math going on here to generate some cost for a playlist. Now note that I just kind of picked this structure. The structure is very arbitrary. This function, this cost function is very arbitrary. A lot of decisions I just made just by kind of making them up. So this one you have to build to get credit, to earn credit. But I do recommend that if you are done with the assignment and you want to just play around with this, play around with different cost functions and generate playlists based on whatever criteria you decide. So I'm saying a lot of variance in the energy between songs. Maybe you want a playlist with just songs that are very high energy, and you want to just reward high energy songs instead of a variance and variety of energy ratings. Play around with the cost function and get different playlists. When you get your AO1 done, at least, you can get different playlists based on different cost functions. The genetic algorithm will optimize based on different criteria that you give it, instead of just the default one that I give. But that's the one I give. I mostly did this to make sure that it's very difficult to brute force the playlist. I want some measure that's difficult to brute force. To brute force this, you would have to try every possible combination of songs in a playlist, or you have to try to come up with the math to figure out which songs are going to maximize both the standard deviation of the energy ratings and the overall rating, overall costs, minimize the overall cost for each song simultaneously. That's tricky to do. I wanted this tricky enough that you see some value in the genetic algorithm, because the genetic algorithm, we don't care how tricky it is to compute something. We just jam it in the genetic algorithm and a good solution comes out the other end. So that's why this is a little tricky to compute. If I just gave you this as a question, find the best playlist based on this cost function, that's tough. But we'll throw it in this genetic algorithm that you code in AO1, and it's done. I feel like this project is being due way too early. I mean, you might only feel that because I gave you an extra week for Project 2. I gave you extra time on Project 2. And this semester I changed the homeworks to 1 every 2 weeks to 1 every 3 weeks. I don't know. I don't think I'm going to field any complaints about that. I mean, I only have 4 projects, and they're spaced out as much as they can be. I don't know what more you want on that. Yeah, and exactly, recovery plans. Everybody gets deadline extensions as long as you've shown some effort in the course. So you're talking about a checkpoint. It's not even a deadline. So if you look carefully at the syllabus, at the learning objectives, concurrency. Well, we talked about the lecture task so long. Let's remind ourselves of what we're doing here. Concurrency and actors. Concurrency, actors, and WebSockets. WebSockets will be introduced Wednesday, and then Friday I'll give examples of these. Friday will be an examples day. You're not required to write any code using these topics. So everything you see this week, I will not ask you to write any code. I will not require you to write any code using these topics. By require, I am reserving the right. I probably won't do this, but just in case I do want to, AO2 of homework 4, the 4th project, might have some actor stuff, so that's not strictly required. I probably won't do that anyway, but I made sure to use the word required here just to make sure it's not on the required path to passing the course. So you're not going to be required to write any code using these topics of this week, but they will show up in your interview and quiz. So you are expected to explain these concepts, specifically concurrency. We are going to ask, what's the deal with concurrency? That's probably going to be one of your lecture interview questions next week. It won't be worded like that, but it'll be like, what is the deal with concurrency? Why do we care? Why would we ever do that? It's probably going to be something to that effect, one of your questions. And then maybe something with actors, like how do actors get the job of concurrency done would be a good one. How do WebSockets get the job of concurrency done? Like what do they use? What do they do? some basic information about those. And then read. You are expected to read code that uses actors. I'm not going to give you a WebSocket question on the quiz, but I will give you an actor question on the quiz. You can count on that. That you'll have a recursion, you'll have immutable objects, you'll have an actor system that you have to read on the quiz. So that's what you're expected to do. I want to make sure that's super clear. So hopefully this slide is helpful for when you're studying. That's what you're going to have to do. Notice the only time WebSockets even comes up is in the interview. So I'm probably going to make sure there's one question on there that's specifically about WebSockets, because that's the only place where I'm giving myself a chance to test you on it. How would a question on concurrency look on the quiz? I'll give you a code for an actor system, and I'll say what happens in this code. So let's learn what actors are and what concurrency is. So most programs we've written so far execute code sequentially. We can have data structures, not data structures. We can have control flow, our conditionals and loops, to change the order in which things are executed. And that order can even change based on the specific run of the program. So if we have a conditional, sometimes it'll be true, sometimes it'll be false, and we'll branch out. And we had these diagrams, these flowchart diagrams in 115 that showed how code executes throughout our program. And everything's nice, everything's simple. We can run a debugger easily and just step line by line through our code. But what if we want multiple pieces of code to run at the same time? Now, hopefully the first question, unless you already know the answer that you're having, is why would I ever want to do that? That's crazy. So you actually had a few situations where you did have code that ran at the same time, different pieces of code running at the same time. In 115, you wrote a web server. To write this web server, you had certain paths that a user could request, and then you gave it callback functions, and you said if the user makes a request for this path, call this function. Run the code from this function. Whatever this function returns, that's what you're sending back to the user. Well, what happens when two users visit your site at the same time? What if I open up two browser tabs and reload them both at exactly the same time? And what if you have, say, 1 million users all requesting access to your site at the same time? Well, how do you handle that? Well, the answer is concurrency. What you don't want is for all the users to enter a queue. What you don't want is the first user, because they do enter a queue. That is how web servers work. But you don't want the first user to make a request. And if the second user makes a request, well, if your program can only do one thing at a time, you don't want your program to miss that request of the second user. You don't want that second user to be flat out ignored. You don't want that to happen. And yeah, repetition. This is the same as asynchronous. It's very similar. You could have asynchronous code that is not concurrent. Is that true? I think that's true, but you'd have to code it in a really specifically kind of awful way. But asynchronous code, typically we use that to enable concurrency. So if our server's ignoring all requests that are coming in while our code is running, handling one request, it's not going to be a usable app. Two people can't use your app at the same time. So what we want is concurrency. There can be a queue where people are just waiting in line, and your code has to do two things at the same time still. Handle one request while having other code maintain this queue of how the requests were made, and keep track of all the requests that still need to be responded to. That's still concurrent code. Ideally, what we want for web servers is actually processing multiple requests simultaneously. I believe Bottle doesn't do that by default, actually. But that's ideally what we want from web servers, is handling multiple requests concurrently. But even without that, you have to have some concurrency. Anyway, I could talk about web servers forever. Let me just move on. We also saw GUIs, where your app has to do multiple things at the same time. Mainly listen for any key presses. And we did this with events. We had events that were occurred, the keys that were pressed, the mouse buttons that were clicked. And we added listeners to our classes that listened for these events. And then whenever that event occurs, we're running a certain piece of code that we've written. So that code can be executed concurrently if somebody presses a button and clicks at the same time. Say somebody's playing jumper with their friend and you're hitting left arrow and your friend's hitting D to move right. You're both going to be able to move because that code's running concurrently. You're not blocking the other user's inputs when you're hitting your inputs. That's not how that works. It's handling those inputs concurrently. And instead of saying run this code, then run this code, then run this code, we're saying when this event occurs, run this code. When the user makes a request for a specific path, call this function. When the user presses a certain button, call this method. Run this code. And in that we have an event-based architecture, which used to be the name of LO5, which doesn't exist this semester. But event-based architectures is the overall theme of how we're getting concurrency in 116 at least. Okay, so for both of these examples, we use libraries that hit all the concurrency. But what if we want concurrency in an app that doesn't use one of those libraries? We don't want to import a web server, or a web framework, more specifically, or a GUI library if we don't have a web server or a GUI that we're writing. That'd be silly. We're not going to pull in those libraries just to get concurrency. So we want concurrency without those libraries. We are still going to pull in a library, but it's going to be a more stripped down just concurrency library. Something that a GUI or a web server would be built on top of. So we'll get the more core library here. We're going to use this by pulling in an actor library named Akka actors. And that's what's going to get us our concurrency at the very stripped down bare level, without having extra code in a library. So the Akka library, not included in Scala, though it used to be and then split off. But now it's not part of Scala, so we have to add it to the POM. If you've been using the same POM from my examples repo all semester, you already got it in there, and you've had this linked to all of your projects. So we install this library. We're installing it through Maven, running Maven. It's installed, it's there, and then you can start using it. This library is going to give us... I'm either a different breed or I'm just pissed. I missed some chat here. What am I mad about? The structure this semester is softer than it has been in the past. I wouldn't say I'm mad about that. That's not something I would do if I was just mad. So And when there was an LO5, there were 6 lecture questions all on actors and WebSockets, where you had to write 3 lecture questions about actors and 3 lecture questions about WebSockets, and then a homework assignment about actors and WebSockets where you write a big app using both. All that's gone. Like, I don't know if I'm gonna have much sympathy about the projects this semester. Not to say that they're easy this semester, but easier than they have been. So this is how we're going to get concurrencies, through this actor library. And what we're going to do is create what's called actors, add them to an actor system. Oh, and there's no group projects anymore. Man, now that y'all mention it, I think I've been cutting too much. I probably should add some. Maybe I'll add a final project in the last 2 weeks this semester. So we create an actor system, and then we add actors to that system. Each actor is going to be able to run independently of the other actors, and they're going to communicate by... Now you're good. Yeah, I thought so. And then they're going to communicate by passing messages to each other. They're going to send messages to each other, and then when a message is received, based on the type of that message, it's going to execute different code. No, I do like the structure this semester. I'm joking when I say that stuff, obviously. I think the structure was a little too intense in the past. So, but I don't think there's anything more I can cut from this semester. And it's not like I've really cut anything. I just kind of compressed them, organized the content better, and I think it's fine. And there, by the way, there is a final project in this semester. It's the project contribution. And it's effectively optional because you can get AOs from elsewhere. But the final project morphed into the project contribution. Your final project, you're working as an entire class, is a team, and you're contributing to a common project. That's the group project. That's what it ended up being over the years, after changing over the years. But that used to be the group project. That's what replaced it. Cut project 4 for another spring break. So, I already said all that. Let's get into the good stuff. So, to do this, first we need a couple more Scala things. Case class and case object. I couldn't think of a better word there. I don't know. Types of types. But these are different ways to create Scala types. A case class is just like a class, except it typically doesn't have a body, though it can. We typically don't use a body. That's not what we use case classes for. And case classes have a few differences from regular classes. The big one that we're using here, or that the Akka library is using, is that these are compared by value and not by reference. They're usually used just to store a particular value. Here I have a case class, which is going to be used to create by equipment objects with an equipment ID. I'm just using this as kind of a vessel to be able to store an equipment ID. And if I have two objects of type by equipment, and I say, are these equal to each other using equal, it's going to compare them by their equipment IDs. And in general, case class, objects of that type are going to be compared by all of their constructor parameters. That's how they're going to be compared for equality. Normally, regular objects, they're going to be compared by reference. Do these two variables refer to the same object on the heap? Case object or case class is going to give us a better dot equals method, and that's going to help us. It's going to help Akka organize their stuff a little more. Of course, you can pass regular classes too, but it's going to help us organize our things. So we're going to use case classes, then case object, same thing except no constructor, and it's mostly used to just signal that an event has occurred. So case object setup, if I send this, by the way, these are used for messages in our actor system. If I send a message of type setup, I'm just saying, hey, start your setup. I have no information to add to that. Just start your setup process. So I'll use that as a case object because there's no specific information I need to send along with that. For a by equipment object, I'm going to say by equipment and by this specific type of equipment. Which I'm kind of sad going through these lectures. The clicker homework is the one that was cut, and this is where we would buy a specific equipment ID in our clicker game. It's 3 AOs on the final. So here's the setup. I'll go through a quick setup, explain the structure, and then we'll hop into an example. So to define an actor class, we're going to bring back some OOP. And get ready for these examples. We're going to use OOP and FP in the same code. It's going to blow your frickin' minds. So we're going to create a class just like any other class, except we're going to extend actor. The actor class has a receive method with a little bit different syntax here. A receive method, which is going to which is going to comprise of a case statement, which is going to check which type of message was received. This will be called whenever this actor receives a message. We're going to check which type that message is and do something based on the type of the message. If that message is a case object, we're just going to say if case object type and then do something based on that. So if we receive a message of type object, there's no information attached to that. We're just going to do whatever we do when we receive a message of that type. If we receive a message that's a case class, that means we're concerned with the information in that case class, and we're going to use our function syntax here. We're going to name a variable of type the message that we receive, and then we can access the actual content of that message on the other side, in the other side of our arrow here, in the other side of our, in the body of this case statement. So if it's a case class, we're going to declare a variable. If it's a case object, we just specify the type. And this can be read as a big if, else if block. If this is the type, do this. Else if this is the type, store the message in a variable, and then do this. Else, nothing else. When we want to actually create an actor, we're going to create an actor system. It takes a string, which is the name of the system, which is just any name you choose for your system. And then we're going to use this actor of props class of. We're going to use this syntax to create an actor. This line is going to create an actor, add that actor to our system, and returns a reference to that actor, which is of type actor_ref. This is a reference to an actor. Whenever we have a reference to an actor, we can send it messages using this exclamation mark method. That's the entire method name. Is one character, and it says actor send this message to the actor. These are both. Actually, I think I messed that up, didn't I? Another message type. Another message type should take a string here for the actual message. So there should be parentheses and the string that's actually being sent. So this is how we send messages to an actor once we have a reference to that actor. Now let's unpack this line. There's a lot going on here. So to add an actor to the system, we're going to take the system, call its actor of method, which is the method to add an actor, create an actor, and add it to the system. We're going to use the props class, create a new props. Its constructor is going to take a class. We're going to pass a class to this method. To get a class, we're going to use this class of, which is a built-in method in Scala. We're going to use class of, and then as a type parameter, give it the type of the class of the class of the actor that we want to create and add to this system. Hope I'm not the only one that's sort of lost here. No, that should be normal right now. There's a lot going on. Remember, keep in mind that you have to understand this to a different level of the rest of the content of the course. You have to Ren, get out of here. You have to understand this to the level where you can read the code, not write the code. So it is a bit different level of understanding. And we're about to go through an example. Yeah, Ren, stop it. Ren, if you're confused... See, the problem, Ren, with you saying that is now I assume everybody's trolling. I don't think that's the case, but you can't joke around with that because I know you understand this stuff. But now, who do I believe? If I know, maybe that's just the culture y'all are doing right now. Oh, we all just say we're confused now. Look, Rin did it. I'll do it too. So now who's trolling, who's not? You can't do that. So this is going to create an actor of type myActor, add it to the system, and return a reference to that actor. You can't create an actor. I mean, you can, but you can't add it to the system. You can't create an actor and add it to an actor system using the new keyword. That's not how we create actors. We're going to use this props class of actor of. We're going to use this syntax. This is always the same syntax except for the name here. So if you don't want to think about this or memorize it, when you see this on the quiz, just know, oh, that's that long confusing line, and here's the type that's being created. So that means Jesse on the quiz is creating an actor of this type, adding it to the system, and now we have a reference to that actor. Blitzkrieg, you really asked that during lecture? I saw Ren's message. I'm like, well, I wonder what the question was. You really asked that during lecture? Didn't you sign up using my Calendly? Like, you chose that time. And also through Calendly, you can reschedule that. You don't have to ask me. unless you're talking about lab itself. If lab itself, no, you can't reschedule that because your other instructor shouldn't be scheduling during another class time. Take it up with them if they're scheduling an exam during that time. If your actor takes a constructor parameter, here's another actor that takes a constructor parameter n. We're going to add that to the call of props. So this is the same as saying new my actor of 10, except when we're adding it to the actor system, we have to use this syntax because props is going to take this class, and inside props is going to call new and take the constructor parameters that you provide and use those for that call to new to the constructor. And you're going to follow up. Dude, ask after lecture. So let's see an example of all this. Like, that's everything you need to know about actors, but that doesn't really, you should all be confused right now. If that wasn't the expectation, I wouldn't have this example that I'm about to show. So let's see an example of this and see if we can make some sense out of what we just saw. So in this example, what we want to do is create an actor class that's going to count down from 20 as fast as it can. That's all it's going to do. It's not interesting. It's not exciting. But that's what we want this thing to do. We're going to create an actor. When we send it the start message, it starts counting from 20 down to 0. And we want to create 3 of these and have them all count down simultaneously just to make sure that we have concurrently running code. So here's our class, which we'll talk about. Before we talk about it specifically, we're going to introduce 4, I can count, I swear, 4 case objects. So we're not going to have any case classes in this example, but 4 case objects, which we're going to use as events that occur, specifically sending messages to an actor. So we have the object start, is done, done, and not done. And how we want to use these objects is when a counter actor receives the start object, it's going to start its countdown. It's going to start at 20 and then count down all the way to 0. If it receives the is done message, it's going to check if it's done or not. If it's done counting, if its counter is at 0, it's going to send back a message of type done to whomever asked that question of it. If it's not done counting, if it's still counting, it's going to return a message of not done. And that's it. That's the whole thing. I don't know why I have the wrong cadence there. Yeah, now Rai Solly doesn't trust you anymore, Ren. Not because of what I was saying earlier, but because you said 2. You must have said 2 AOs on the final. So we have our code to count down. What I want to highlight here is that this is a regular class, just like our comparators when we had. Did we do comparators? No, our listeners, our event listeners back in GUIs. They're just regular classes. We can do whatever we want with them, with our classes. Our states for our state pattern, those were regular classes. We can do all our class stuff with them. That includes adding constructor parameters, adding helper methods, adding state variables. All these things are perfectly valid things that we can do. He said 3? It is 3. 3's the number of AOs on the final. So this code, this countdown helper method is going to check if n is greater than or equal to 0. We're going to decrement it. So our n actually does end at -1 if you're paying close attention to this code. It's going to check if n is 0 or positive. If it is, print out the current value of n with the name of this specific counter and decrement n and call countdown again in our good old recursive fashion. If the counter has reached 0 or has reached -1 technically, we're just going to say print to the screen, this counter's finished. So nothing fancy here. I just want to emphasize the point that just because we're extending actor doesn't mean we can't do all of our regular class stuff. This is a regular class. We can do all the class stuff that we want. Constructors, state variables, methods. Except we also, since we extend actor, have to implement the receive method to define how this actor responds to messages that it's being sent. So the receive method, which will always follow this syntax, and then the cases we'll write, well, I'll write and you'll read, will follow this structure. Case start means run this code whenever you receive a message of type start. So whenever we receive a message of type start, we're going to set n, the state variable, to 20, and we're going to call countdown, start the countdown. Oh, is there a var in here? There's no var in here. Oh, yeah, there is a var in here, the state variable. That'd be easy enough to change, too. You know, I could change that easy enough, but I think why I did that is so I can show that there's a state variable, that we can have state variables. And state variables are kind of pointless if they don't change. Report me. I can change. Hey, if after lecture you want me to change this to not use a var, I actually do want to. There's another way to write this example which I like better, but it doesn't show as much of the stuff I want to show. I can rewrite it that way, which does avoid var after lecture. So when we receive a message is done, we're going to check the state variable n. Oh, actually, we couldn't do the is done. We do rely on state here. This example does rely on state, doesn't it? For the is done method, we're going to check n. If it's less than or equal to 0, we're going to send to the sender. So whenever we receive a message, we always have access to the sender. This is an actor reference to whomever sent this message to this actor. So whenever we have a message received, we have access to sender. This is an actor ref to the sender, and we can send them back a message. So whoever sent this to this actor, send back to the sender the message done, to say, hey, I'm done. Here you go. I'm done. Just letting you know. If we're not done, same thing, same syntax. We're just going to send a message of type not done based on our case objects that we have here. These are the message types that we have available. This stuff is hard. Yeah, but I mean, sure. Yeah, sure. It is hard, yeah, and you need a refresher. I guess this is your refresher. I was going to say you have to refresh it by the end of this lecture. So as long as you can get it by the end of this lecture, that's fine, I guess. Because it's eligible for a lecture for office hour questions after today. And you better have answers for students. But as long as this lecture is your refresher, that's fine. So now let's take our counter class. I cut out most of this, just highlighting the start message, what it does when it receives the start message. In creating a system, I'm going to create an actor system. Same syntax we used before. I'm going to create 2 or 3. I promise I can count. 3 counters. I'm going to add 3 separate counters to the system. I'm going to name them 1, 2, and 3 through its constructor parameter. And I'm going to send all 3 of them the start message. Where does is done, start, done, not done come from? So this will be somewhere in the code. I believe we're about to go to the code anyway. I'll show you in the code. Did I forget exactly where I put them? Yeah, I put them right here. Okay, right in the concurrent counters class. Sometimes I like to put all the message types in a separate file. For this one, I put them just in the concurrent counter class, or in the counters. Same file as the counters. But you do have to declare these somewhere. These have to be defined somewhere in your code. So you can send messages of your custom message types. And I have my my Akka, actually that's not even Akka, my Akka stuff imported. Same code we saw in the slides. That one we haven't seen yet. Same code we saw in the slides. Let me get rid of this part. And this is the same stuff we saw in the slide. So what we want to do is run this thing and see what we actually got when we run this. Remember, each counter is going to print out as it's counting down. It's going to print its name, 1, 2, or 3, and the current value of n as it's counting down. So let's take a look at this. When we add 3 of these counters to an actor system, and tell, oh, come on. And we're going to tell counter 1 to go, counter 2 to go, and then counter 3 to go. So let's take a look at what we actually get. Counter 1 starts its counting at 20, and then right away, the very second thing that happens is counter 3 starting its counter at 20. So even though we sent this message to actor 2 first, since we're running concurrently, all these things are happening at the same time. Once this message fires off, we don't really have control over how that executes. We know what's going to happen. We don't know the order. We're going to fire off this message. We're going to fire off this message. And then it's up to the system and up to all kinds of other factors to determine which order things are going to be processed. So 1 got the message first and started its processing. 3 started next. And then 3 actually gets all the way down to 15 before 2 even starts counting at 20. 3's down to 14. 1 finally says, okay, I'm going to count down to 19. And then so on. We can see all of these 3 counters are counting concurrently. This is happening simultaneously. We have 3 things happening in our code at the same time. And it looks like the pace 3's been going at. It looks like 3 is going to be done first. Even though it was the last one to start, 3 is going to be done first. 1's going to finish next. And 2's going to finish last. 2 only got to 14 before the other 2 were finished. Now let's see the heap and stack. I'm not going to ask you to do stack and heap for the concurrency questions. I always wanted to. I want to do that someday in this class, but not this semester. We could kind of do, you can infer some of the idea what's happening on the stack and heap, but it gets choppy. And if we rerun this, we're going to get a different order. This time 1 finished first, then 3, then 2. So these are happening concurrently. These things are happening at the same time. We cannot predict the order. Once things start happening, they're just happening. But this method, this countdown method here, we have 3 instances of this method running simultaneously. They're all running concurrently. We have concurrent code. We've successfully written a concurrent program. That's the key thing here. Then along with that are a lot of implications. Most of those you'll start exploring in 220. We're not going to go too far. I just want to drive home the fact that we can have multiple things running concurrently in our code. That's your big takeaway for 116, and a little bit of an idea of how that might happen through these actor systems, message passing, and event-based architectures. I won't ask you stack and heap. I know that's the way it's worded in the syllabus, but I'm not going to go there with concurrency. Mostly because how do I highlight a line? If I highlight a line and say, what's the state of the stack and heap at this line, I either have to be very specific about in which actor, at which point, after which messages, how do I actually say when we have multiple things happen at the same time, what does it mean to hit that point? There could be a lot of different answers. Or I put that after all the fun action happens, and then it's just a regular question about stack and heap, which isn't interesting. It's not new at that point. Now I'm going to ask you stack and heap about recursion mostly. That's where I want to see your stack. I want to see all the recursive calls on the stack. That's where I'm going to ask you about memory. And also immutable objects. When you create change an immutable object, the fact that it creates a new object on the heap, that's what I want to see. The actors I'm not concerned about. So let's create another actor class. I'll go through this one in a minute. Another actor class which is going to supervise our counters. It's going to take a list of actor references as its constructor, which is absolutely something we can do. And it's going to check whenever it gets the update message, check all of these actors, whether they're done. And here's where we're going to see some FP again. For each actor in this list, send that actor the is done message. And then if you receive a message of done, check if the sender has already been added to the completed list. If it hasn't, then add this one. Say this counter is complete. And then if it's not done, say, oh, not one of the counters sent me back a not done message, so that one's not done yet. We're going to add that to the system. Its constructor parameter is a list of actor references, so we can create a list of these actor references that we have. And now this supervisor is going to supervise these 3 counters and check when they're done. And to do this, we're going to send it. The supervisor, I'm not going to put this on the quiz, so I'll just blow through the syntax real quick. But I'm going to send the supervisor twice per second the update message to have it check on the 3 actors, these 3 actors, as they go. Oops, I didn't want to do that. What am I doing? There we go. So if we run this again, with our supervisor in there, it's actually just going to say that they're all done. It's going to check if all those counters have finished or not, and they have finished. So the supervisor gets the update message. The supervisor sends the is done message to all 3 of the counters. The counters receive the is done message, sends back to the supervisor the done message. The supervisor receives the done message and then runs this code to add them to the completed list. Once that 3rd counter returns with the done message, the completed list size is going to be the same as the total number of counters. So we know that all counters are complete and can print out our all counters complete message. But we're sending a message which triggers messages to be sent. Those messages send messages in response. These counters send messages in response. Those messages send here, and then we get some code executed. So you can see how these messages are being passed across actors. This actor is sending a message to another actor, which is sending a message back using the sender. Whoever sent this to me, send them the done message. We're getting the done message here and running this code. So it kind of creates some spaghetti code. You have to trace through it a bit, which makes it fun for quiz questions. But as long as you follow the messages, you can find out what's going to happen in each code, in each actor. So the supervisor gets update, sends is done, ends up returning done, and then run this code.